all the examples we looked at to start with had all of our velocities travelling in the same direction. In order to be able to get to explosions and to be able to understand how we apply conservation of momentum to explosions, we need to first of all understand what happens to velocities when they're going in different directions. So what I started off with was showing you an example where you've got two people approaching each other with velocities in different directions. So just as before when we were looking at like velocity time graphs and things like that, and even projectile motion, if we've got a velocity in one direction, we consider that to be positive, and if we have a velocity in the opposite direction, we consider that to be negative. So here we have the velocity that's going to the left as being a negative value. That's crucial here because that will help us to figure out what this velocity and in what direction that velocity is going as well. So as a general rule, we take going to the right as being positive and going to the left as being negative. Normally to the right is in the forwards directions in these examples. But as usual, it doesn't matter which one you choose as being negative, as long as you choose one of them as being negative so that you can display that it is going in a different direction. So we apply the conservation of momentum to that collision using this equation, which we must remember. We don't get given that in the equation booklet. We apply that there, and notice the difference here. We've got a negative number there, so that negative number has an effect on what our final answer is. So we find out 0.43, so it's a positive value, 0.43, so therefore it must be going in this direction. The logic of giving the velocities a different sign is really crucial to your understanding of explosion type problems, which is what we moved on to after that. The difference with an explosion type problem is that the majority of the time all parts of the momentum system are initially at rest, so they're not moving to start with, which has impacts upon your conservation of momentum equation. So we used a gun example where the gun and the bullet are together to start with. The bullet is fired in what we assume is the forwards direction, so we take that as being to the right hand side and therefore being positive. We have to calculate what the recoil of the gun is given the information that we have. So again, it's the same equation here, but what you'll notice is different is that the whole left hand side of the equation is 0. So there's no momentum before the collision because there is no velocities. There are no velocities before the collision, so although we have mass, we have no velocity, initial velocity, so no momentum. We equate for V1, which is the velocity of the gun, and we find that it comes out as being a negative number. It comes out as being negative 0.4, so therefore it must be going in this direction, which is what we would expect from recoil. It's a bigger mass, so we don't get as much velocity. Remember, velocity and momentum are two different things. Momentum is a product of mass and velocity, whereas velocity is just velocity on its own. You need to consider how much the mass is and also how much the velocity is to figure out the momentum of something. So don't get those two things confused. So we find out that that's a negative value. Again, we're applying to the right as being positive, to the left as being negative. Provided you do that, then explosion problems shouldn't be too difficult. You see why it needs to be negative because we need to basically equate this right hand side of the equation here to 0. So this term, this first term, term 1 if you like, must be equivalent to term 2. So it's going to have to be the negative of what this is in order to make sure that we get 0 before and 0 afterwards.